It's turned on, yeah.
Okay. Good afternoon, ladies and gentlemen. In the next 20 minutes before the panel discussion, I was going to bring you up to date on the status and future plans for full simulation and reconstruction within the North American Linear Collider detector environment. I'll touch on some aspects of internationalization, some plans for future efforts, and hopefully some of this will spark your interest and ask how you can get involved in this. So let me just describe once again, you've heard all day today about simulations, and unfortunately for the next 10 years, we will be doing simulations, except for perhaps detector R&D and test beam. So it's an important aspect of our studies. As was mentioned before, we do need to cover the full aspects of expected and unexpected physics in the 1 TeV regime. We'll need to perform precision measurements of complex final states, and will require, as you heard in the previous detector sessions, exceptional momentum resolution, 10 to the minus 5 or so, very high efficiencies, excellent vertexing capabilities for flavor tagging, energy flow calorimetry, and hermeticity, and this with allowances for new technologies, new algorithms, and smarter graduate students and postdocs in the next decade. So what's our mission statement for the simulation environment? Well, clearly we need to provide the full simulation capabilities. We need to be able to do everything from generating events through to detector design simulations and reconstruction and analysis until you get to your final histogram with the peak in it that you publish on HEPX. We need flexibility, obviously, for the new detector geometries and technologies. I think Keith listed 4 transparencies versus full of different technologies. We have to be able to handle that in a combined environment. We need to allow for different reconstruction algorithms. We need to allow for energy flow. We need to allow for canonical jet finding, etc. And in the future, I hope that funds will be released for detector R&D, and so we need to be able to account for test beam setups as well, so that we can, within the same framework, model the detector and model the test beam setup. So let me now, having said all that, tell you how we hope to accomplish this with limited resources. We have to have efficient solutions, and we have to have focused efforts. And my first way to see how to do this is to triple our effort by incorporating the Asian, the European, and the North American environments into one environment. I think as experimentalists, we can remain agnostic about the technology choice for the accelerator per se. To first order, I would argue that the technology and the siting of the accelerator are relatively unimportant to the physics. To the sociology, you can argue, but I would say to the physics and to the simulations at this level, it's relatively unimportant. At best, one collider is going to be realized. The linear collider community will coalesce, and I would argue that it would be best to do so earlier than later. And so we've been making efforts within the 3 regions, within the simulation groups, to work in a more coordinated fashion in order to share, and of course, as a reward of working together. The recent focus for the North American group has been, for this last, for the 6 months of 2000, gearing up towards the Snowmass meeting. It was hoped that we could attract interest amongst the attendees, the 1,200 attendees who were in rarefied atmosphere for 3 weeks. We hoped we could convince them that this was an interesting opportunity to get involved, and as a result of that, we produced a software resource CD, which included essentially all of the tools for somebody to come wet behind the ears, knowing nothing about linear collider environment, and actually do analyses at 8,000 to 10,000 feet. And I think we were fairly successful. There were several analyses actually presented at Snowmass that started from scratch and went to peaks and distributions. So I think that the existing structure and framework already allows event generation and fast detector simulation to be done. I think we're fairly successful there. And so this is what we had. The emphasis was not on full reconstruction, however, because a limited time of 3 weeks precluded that. The plans for the future are now to switch gears. I come out of Snowmass reading the HEPAP report very encouraged feeling myself that the physics case has been made, I want to now get into the dirty work of designing detectors and really thrashing them out so that we can get the best detector built as possible. In order to do that, we need full detector simulations, and the tool for that is emerging. It is JANT4, and we are moving toward utilizing that in our detector simulations. We want to emphasize, again, results from reconstruction. Smearing 4 vectors, I'm sorry, for me, just does not do it anymore. We need to move beyond that. We need to have full pattern recognition in the tracking system in the calorimeter. We need to actually get an ab initio particle ID, so an electron is not just PDG ID 13 plus a little bit of efficiency. And we need to close the loop in the energy flow jet reconstruction where we tie the calorimeter and the tracker and the whole detector response together. We need to include machine backgrounds. As we push the luminosity, as we push the capabilities of the machine, backgrounds become more and more important. As we push the inner radius of the vertex tracker closer and closer, machine backgrounds become important. We need to do this correctly. And then we need to iterate. We need to push it, find out where it breaks, replace it. As new technologies become available in a year, 2 years, I think even 6 years down the road would not be too late. We need to be able to iterate and put those in and treat them on a fair basis. So we've begun the transition to JANT4. We've incorporated the existing description of detector geometries that we use in our current North American simulations into JANT4, and we're able to dynamically create various detector geometries in one executable. We've defined generic hit classes for tracker and calorimeter hits in an attempt to then be able, for instance, to simply shove the Tesla detector into the North American JANT executable and provide Tees and company with hits that they can reconstruct with their reconstruction. So that there's no question about what level of detector description is in the simulation. There's one executable. This is just for those people in the audience who are worried about detector descriptions, overlaps, things like that. There are various modern computing technologies which allow you to sort of vet the detector geometry roughly at compile time. So when you describe the detector in your file, it does certain amounts of checking to make sure that you're not stepping on volumes. And I think we all prefer a common JANT4 based solution for, as I said, the 3 linear collider regions. So I would suggest that as a step towards internationalization, we could actually be running a single JANT4 executable with a dynamic description of the geometry, so that if you decide at the last minute you want an intermediate silicon tracker between your TPC and calorimeter, or you want an intermediate tracker between your vertex detector and your TPC or your silicon tracker, you can do that. You edit an ASCII code and you run it. It takes no compilation, takes no knowledge of make files, system executables, etc. As I said, it's determined at runtime. We write out these common ideal hits, and we digitize as appropriate with various plugins. So obviously, you can't simulate the response of a drift chamber if you put a silicon detector in there, but if you put in a silicon material in there, you can then at will decide whether it was a 20 micron or a 50 micron or a 2 micron resolution at a later time. I think, personally, as somebody who actually works on this stuff, it's enormous savings of effort if I can be sharing my investment with colleagues across the ocean. I think it makes comparisons easy. There have already been, just today, we've only been meeting for 1 day, and there's questions about, well, I did an analysis, and I did the same analysis, and I got different answers. I think if you have a common framework, common plug-in, it's very easy to resolve questions of comparisons. And as I said, we prefer common solutions, and in this case, JANT4 is or will be the lingua franca for full simulations in high-energy physics. So currently, the North American full simulation environment is a C++ object-oriented environment which uses Gizmo, which most of you have probably never heard of, and that's okay because we're phasing it out to be replaced with JANT4. The European environment, Brahms is the full simulation framework. It's a Fortran-based framework which uses JANT3 as the simulation engine. And similarly, in Asia, the GIM environment is, again, a Fortran calling Géant 3. Now, this is not to say that the regions have not independently started to move towards Géant 4, but there has been little cohesive effort to do that. And in the last 6 months or so, I've met both with my colleagues in Europe and in Asia to, again, further this idea of having one common framework, not even a framework, but a common executable. So that, as I said, at will, you can change the geometry and not have to worry about any of the internals. So having simulated the detector response to the physics events that you've generated, you need to be able to analyze them. And the North American group supports 2 modern object-oriented analysis frameworks. We're trying to be as inclusive as possible. Once again, the idea is to bring in as many people as possible to lower the threshold to contribution. We support a root framework developed not at CERN, but in Europe, definitely, and used now in both of the collider experiments at Fermilab, being used at Bavar, being used at more and more high-energy physics experiments around the world. And we also support a Java-based analysis framework within the Java Analysis Studio, also known as JAS. Within those 2 frameworks, you find roughly equivalent functionality in terms of your standard algorithms that you would expect to be doing in high-energy physics reconstruction, jet finding algorithms, invariant mass, vertexing, flavor tagging, etc. Those are all available. Indeed, those are all on the CD for your sort of personal edification. There are, of course, displays for event visualization. You want to make sure that if you've made a drastic detector geometry description, you want to be able to look at it. Of course, you need visualization for that. And, of course, the usual slew of histograms, fitting, etc. Here's an example event display. You saw one earlier as well within the root environment. This is an event display within the JAS environment here, concentrating on the calorimeter tracker, showing tracks, vertex detector hits, etc. There's also a connection made to the 3D wired event display, which was developed at CERN. It's fully incorporated within the LCD analysis framework. Particle ID is, of course, very important to linear collider analyses. And in this case, I don't mean Ks and Ps and electrons and muons. I mean Bs and Cs and gluons, things of that nature. And how do you do that? Vertex tagging, flavor tagging of the jets themselves. Topological vertex analysis, which was pioneered at SLD, has proven to be very powerful in terms of doing B tagging, C tagging, and even discrimination between B and C in the same events. And that's available, again, within both analysis frameworks. And you'll hear 2 talks on that tomorrow. I believe one's during the vertexing and one is during the simulation. And these are just things that you can do. You can do PT-corrected vertex mass. So on the left, you can see even there, just taking the mass of the vertex that you've reconstructed gives you very good BC separation. And on the right, you can actually see vertex charge so that you can tell the B plus from the B minus in the event. This is just a sort of pastiche of things that are available, event displays, histogramming, fitting, etc. And as I said before, we've stressed roughly equivalent functionality within both a C++ or a Java analysis environment. So how do we encourage participation? How do I get even 10% of you, 200 some odd physicists, to actually contribute and help us develop the detector for the linear collider? The tools are in place for many of the analyses. You do simply want to do event generation, fast 4-vector type smearing, reconstruction analysis, peak finding. You can do that already. What I'd like to do, though, is to move on. I'd like to get some help designing the detectors. I'd like Keith to have some of his items on his list checked off by some of you in the audience. I'd like to have some of Ray's concerns about how to integrate the energy flow addressed by some of you in the audience. And I'm not sure how to do this, but I'm thinking that perhaps one way might be to have a mock data challenge for the linear collider and generate a large sample of events and simply throw them out to the community and have you tell me what SUSY is in there or how many extra dimensions are in there. It will clearly stress the current reconstruction, because in order to do this honestly, one has to throw away the Monte Carlo information. And in order to do that, you need to have the full reconstruction. And as you heard in the previous 3 talks, we don't have all those tools yet. However, I'm hoping that having a goal will spur the development of these tools. So what timescale could that happen on? We have many upcoming meetings. On the coast of Brittany in April, the ECFA-DAISY second round of detector and physics simulation meetings will take place. We're talking about having another North American meeting sometime in May or June. The Asian meeting will take place in Tokyo in July. And then, of course, there's LCWS in Korea in August. And I think something like this we could shoot for August and use some of these intermediate ones to flesh out, firm out, A, the desire for that, B, some of the technical issues of it, and C, some of the milestones that we would need to meet along the way. But I think there's plenty of opportunity to continue this at a stage so that every 3 months or so, one knows exactly where one is and where one is going. And this is just how you would do it. We would generate events. We would try to be very careful that you would get the whole slew of events, not just your particular MSSM tan beta spot with no backgrounds and only your favorite signal. We would try to include beam structure with the correct overlapping of previous and post events in the event, including machine backgrounds. We would try then to write out only the detector hits, and we would throw away all the Monte Carlo, and then you would be sort of left to the devices to use the tools that are there. And I'm hoping, again, that the challenge would encourage people to then fill in some of the missing gaps. It would also allow us to focus our effort on specific events, parts of the missing reconstruction. So how would we do this? Well, as I said before, we would generate these events. We can generate them at SLAC. We could probably generate them at Fermilab. We could generate them at other institutions around the US. Although we're in the middle of Collider run, the Babar run, the Clio run, I believe there is still probably some excess CPU and disk space capacity for the very modest means that are required here. We could simulate 1 year, 2 year, and still not come anywhere near the current data handling requirements that are being accommodated. So I think we could still do this. So how would you, as a physicist, access this data? Well, currently, within the JAZZ analysis, we already have the concept of a client server. So the physicist sits at his terminal, at a GUI, does code development, and then you go through the process of debugging, compiling, until you're happy with your particular analysis. You now then connect over the network to a site which maintains the data. You do not ship the data to yourself. I do not ship it to you. We could, but I don't think that's the way we want to go. So you ship, actually, your code to the data analysis engine. And one particular nice thing about Java is that Java is very net aware. It's very security aware. It has its own little sandbox that takes care of security issues. You don't have to worry about it. So then you then do your analysis on this data analysis engine at the remote site where the data is. And then on demand, you transfer the results, and only the results, back to your workstation. There you can have any particular experiment extensions, any plugins, any particular customizations of the display that you want. And in the end, you're one happy camper because you now have a peak in your distribution. And this actually works. This has been going on for years. There will be reports actually tomorrow given by people who have done their analysis exactly this way, remotely, not accessing the data except through this paradigm. Now, how do we extend this? How would we move on if we had much, much more data? Well, the nice thing about having a client server is that you can simply insert in this a control server. To the client, it looks like a server. To the server, it looks like a client. And the control server then has the responsibility for finding out where in a distributed environment your data set is. I say I want to analyze all the data, or I say I want to analyze all of the positive polarization for the electrons data. And the control server will know that and feed your code to a catalog server. And the catalog server will then prompt each server in return, linking it up so that you now have your data analysis running on those servers which have the data that you requested, and to you, it's totally transparent. You're sitting down on your client, you have no idea that any of this is going on. So, welcome to the grid. If you've been hearing about it, in some sense, it already exists. So, let me summarize. I haven't given you proof of this fact, but I would argue that the LCD group has developed a very dynamic detector design, data reconstruction, and physics analysis simulation environment. Many analyses have been done. Many analyses can be done with very little effort on your part, very little cost of entry to actually do an analysis at this level, at this stage. I've only scratched the surface. We'll talk about it some more. You'll hear some more talks tomorrow in the particular subdetector meetings and in the simulation meeting after the coffee break. But it's a large body of work. It's conducted by a remarkably small community of fairly dedicated individuals. However, much work remains to be done. And one reason I'm standing up here in front of you is to appeal to you to fill in holes that you find are missing, or even sometimes simply to point out deficiencies that we may not be aware of because that's not our area of specific interest. And I think the thrust of my particular choice of presentation material today is I think we need to get serious about detector design. We need to do this with realistic backgrounds. We need to do this with realistic analysis. We need to stress the tools that we have, and we need to not be complacent with, as I said before, smearing 4 vectors and doing another recoil Higgs mass plot. So more information can be found at this URL. Binaries, full source, programming interfaces, tutorials, et cetera, et cetera. I have a few copies of the CD. If you weren't deluged with them at Snowmass already, I'm more than willing to hand some more of those out. Here are a fraction, or actually this is most of the people involved. I'm probably forgetting someone for that. I apologize. Any more questions, information, talk to me afterwards or send me email. And that's it. Thank you.
All right, questions?
This is a sort of Monte Carlo question. Several years ago at Snowmass, I remember discussions of a really small diameter high field detector. And I'm curious what would happen with the 5 Tesla detector if you made it a meter in diameter for the tracking volume instead of, about 3 times that. Has that been looked at?
No? You want to do it?
That's our old small detector. We threw that
Well,
out
the old.
time ago.
What goes wrong in terms of the physics output from it? What's the problem with it?
You don't have enough separation in the calorimetry. The opening angles. You need
Okay.
the radius buys you opening.
Was that done with a small Moliere radius like we're talking about now?
Yeah. So that was the old small detector studies. There have been a number of studies that have shown the large detector has a clear advantage over that. Okay. The silicon tries to address that by going out in radius somewhat, by 50% or so.
Okay, thanks.
All right, any other questions?
Okay.
Thank you.